Hello friends, welcome to Mu Lessons. In the previous three videos, we have seen about the DC network theorems. So in those videos, we were generally discussing about the DC networks. Now in this video, we will start discussing about the AC circuits, how to analyze these AC circuits. So here are some steps to analyze the AC circuits. Like first of all, you need to transform the circuit to a phasor or the frequency domain. Then we need to solve the problem using several circuit techniques like the nodal analysis, mesh analysis, superposition theorem, Thevenin's, Norton's. Then again we have to transform the resulting phasor to the time domain. So first of all we will start with the nodal analysis. Since KCL is valid for the phasors, we can analyze these AC circuits by this nodal analysis also. We have to determine the number of nodes within a network, pick a reference node and label each node with a subscripted value of voltage V1, V2 and so on. Now we need to apply the Kirchhoff's law, or you can say we have to apply the Kirchhoff's current law at each node except the reference node. Now assume that all the known unknown currents leave the node for each applications of Kirchhoff's current law. Now we need to solve the resulting equations by the nodal voltages. Suppose there are these are for the dependent current sources. Now for dependent current sources, treat each dependent current source like an independent source when Kirchhoff's current law is applied to each defined node. However, one of the equations are established. Substitute the equation for the controlling quantity to ensure that the unknowns are limited solely to the chosen nodal voltages. So these are some similar steps, or these are some normal steps which we used to follow in case of DC networks also, but the complexity rises with the calculation part in case of AC networks. Nothing else, all other things are quite similar. So this was just steps regarding how to proceed with this nodal analysis. We will go with some new examples so that it will be very clear for this point of view. Since KCL is only valid for these phasors, we can analyze these AC circuits by the nodal analysis. So here we have a question of 10 sin 2t ampere, that is a current source, a resistance of 2 ohm and capacitor of 0.2 farad and inductance of 2 henry is connected in this whole mesh with a resistance of 4 ohm, and here you can see it is a dependent voltage source of 3 Vx. Since the current circuit or this present circuit is in frequency domain, is in time domain, we need to convert into frequency domain. So how can you know this is in time domain or frequency domain? In time domain you can get these values Vm sin omega t in that form. So the current source is given as 10 sin 2t ampere, and that denotes that it is in time domain. So after converting into the frequency domain, we get it as the magnitude is 10 and the angle is 0 degree. So you can use a calculators for the rectangular conversions to polar conversions. This is the polar form. So whenever you deal with AC networks, there are two things important to remember, that is the rectangular form and the polar form. While subtracting and addition, we need to use the rectangular forms, and while divisions and multiplication, it is better to use, or it is always appreciated to use this polar form. So there are several applications in longer networks. So for this present circuit, we have the circuit in the frequency domain 10 0 degree ampere. This is the current source. Now we are having two nodes, that is V1 and V2. You can see from this circuit diagram. Now at node 1, what you need to do is we have to apply the KCL, that is Kirchhoff's current law. So at node 1, 10 is equals to V1 by 2 plus V1 minus V2 by minus J 2.5. So you can see from this previous diagram what happens in case of node 1. In case of node 1, there are two currents that are the one current is going through the node and two currents are going out of this node. So it has been written as 10 is equals to V1 by 2 plus V1 minus V2 by minus J 2.5. So it is quite clear from this figure. Now similarly, after solving this or minimizing it into equation, we get 100 equals to 5 plus j4 v1 minus j4 v2. Now similarly at node 2, the second node where we have a voltage source v2, we can write v2 by j4 is equals to v1 minus v2 by minus j2.5 plus 3vx minus v2 by 4, where vx is equals to v1. Again you can see from the previous diagram, from the circuit diagram, for this v2 how it has been written: v2 minus v1 by minus j2.5, v2 by j4, and 3vx minus v2 by 4. Now by solving these two equations, you can put them in matrix form. The matrix form is quite easy to use. You can use in this calculator form. So after putting all the both of this equation in matrix form, we have to solve simultaneously to get the values of v1 and v2. So v1 we have got is equals to 11.32 angle 60.01 degree, and v2 as 33.02 angle 57.12 degree. Now for calculation of this type of problems, you need to convert it into rectangular form in the matrix form. Then again, while division, we need to convert it into polar form, because I have already told in case of division and multiplications we need to use the polar form, and it is very frequently used and it is very easy. So by using some of these techniques, you can get v1 and v2. Now the final step was to convert the frequency domain into time domain. So the magnitude remains the same, that is 11.32 sine 2t plus 60 degree 60.01 degree in volts. Similarly, v2 will be 33.02 sine 2t plus 57.12 degree volts. So after converting into time domain, our work is complete. So this is the net answer, or you can say the net voltages at the 2 points v1 and v2. Similarly, we come across the next part, that is the mesh analysis. Since KVL is used for phases, we can use AC circuits by this mesh analysis also. Here is given as a bridge circuit. In this case, it has already given in frequency domain, that is 50 angle 0 degree volt for the voltage source, which is connected to a resistance of 10 ohm. Then here is a capacitor minus 4J, inductor of J8, and resistance of 5 ohm, and another capacitance of minus 6J ohm. So now in this part we need to apply the KVL, or better known as mesh analysis. So you can guess what will be the equations. You can write it down. In the next slides I will obviously show the results. So I actually appreciate going through these problems at the time of this video, so that you can know your mistakes if you are making any mistakes. So I would prescribe you to draw these diagrams along with this video. You can draw this diagram. Just I am giving some time, you can just keep on solving these things. So hope you have got some equations in your mind. Next we will follow these equations. Now for the first mesh, that is the mesh 1, we get equation as 15 minus 4j I plus j4 into I2 minus 5 I3 equals to 50. So how do you get this? From the mesh 1, you can see this is the first mesh, I1, current is flowing in this mesh. Here there are 3 elements like this voltage source, 10 ohm resistance, 5 ohm resistance, and one capacitor. So by applying mesh analysis, you can easily find the equations for this mesh 1. Now for the super mesh, that is the bigger mesh, We can write the equations as J8 minus J4 into I2 plus 5 minus J6 into I3 minus 5 minus J4 into I1 is equals to 0. Also from the circuit diagram we can see I3 is equals to I2 plus 2. Now we need to eliminate I3 from these two equations, that is equation 1 and 2. So again, by using some techniques, like we have to eliminate I3, and I3 can be replaced as I2 plus 2, and we replace I3 as I2 plus 2 in these two equations, and we get some new equations, list 4 and 5. Now we will proceed simple as we have proceeded before, like in the matrix form we convert the whole system into matrix form, and we try to get these two values I1 and I2 from this matrix form. Now this matrix form is basically nothing but the determinant form, so you are quite aware in mathematics how to solve this determinant form. Now just see in these two types, while solving this in determinant form you need to multiply these two terms, 15 minus J4 into 5 minus J2 minus 5 plus J4 into minus 5 plus J4. So while multiplying these two terms it will be very difficult on your part, so better to convert into polar form, then try to convert into rectangular form, and after that again the net resultant will be subtraction of two terms, then you can easily do the subtraction in rectangular form, and finally the result is to be written in polar form. So the result that we got is 58.86 and the angle is minus 9.78 degree. Now similarly I1 we can get by solving this in determinant form. So I0 will be I1 equals to delta 1 minus delta 1 by this delta. So I0 equals to 5.074 and angle is given as 5.94. Again this is in frequency domain, you have to convert it, if it is required you have to convert it into time domain. The magnitude will be same, you just need to be concerned about this phase difference. Now the next theorem is about the superposition theorem. This superposition theorem holds same for this AC circuit as we have studied in the DC circuit. The superposition theorem eliminates the need for solving simultaneous linear equations by considering the effect of each source independently. That means we will consider the effect of each source independently, and afterwards we will combine its effect to get the net resultant. To consider the effects of each source, we remove the remaining sources by setting the voltage source to 0. That means how can we set the voltage source to 0, or how can you deactivate the voltage source to 0? Just by short circuit representation. Now the next question is how to deactivate this current source, just by open circuit representation. Now again the current through or the voltage across a portion of this network produced by each source is then added algebraically, and to find the total solution for the current or the voltage, whatever is required according to the question. Now there are some points. I think you are getting bored with these points, but these are some certain points, key points to remember. Then we will proceed for the numericals. The only variation in applying this superposition theorem to AC networks with independent sources is that we'll be working with impedances and phases. The superposition theorem is not applicable to power effects in AC networks. You have to keep in mind this superposition theorem is not applicable at all to power effects in AC networks, since we are still dealing with a nonlinear relationship. It can be applied to networks with sources of different frequencies only if the total response of each frequency is found independently and the results are expanded in a non-sinusoidal expansion. One of the most important applications of this superposition theorem is electronic circuits, in which the DC and AC analysis are treated separately and the total solution is the sum of the two. So this is one of the practical applications where the superposition theorem is actually used. Now for this superposition theorem, when a circuit has sources operating at different frequencies, we need to separate the phasor circuit for each frequency and it must be solved independently. The total response is the sum of time domain responses of all the individual phasor circuits. Now here is some circuit diagrams. You can see the superposition theorem applies to AC circuits as well. For sources having different frequencies, the total response must be obtained by adding individual frequencies in time domain. Now, superposition techniques for this source different frequencies, like in this case we have two voltage sources, 10 cos 2t and 5 volt, and one current source, that is 2 sin 5t. Now in this we are dealing with two different frequencies. So for the first attempt, all sources, we have to consider all the sources except 5 DC, 5 volt DC is set to 0. That means all the other sources, that is this voltage source and this current source, has to be deactivated. This voltage source can be deactivated by short circuiting, and this can be deactivated by open circuit. So in this case we are considering only the sole effect of this 5 volt DC circuit. Similarly, in the next part we'll deactivate all of the sources except the first part, that is a 10 cos 2t. Now in the third part we'll consider only the current source and we'll deactivate the rest too. Now after doing this three analysis, we will find the current or voltage required in 3 steps in the 3 different circuits, and we'll find total the sole resultant of the circuit. Now here is in question. I hope you don't follow this solution. This is a task for the next video. So this is a question. You need to find I0 in this part. You need to find this I0 using the superposition theorem. We have already done these types of questions in superposition theorem of DC networks, so I hope you have gone through those videos. So this is, you can say, a simple test for you, whether you have checked yourself very correctly regarding this theorem or not. So I hope you liked this video. We will be discussing about the solution to this question along with the application of some more theorems on AC circuits in our next video. So that is not important. The most important thing is how can you solve this part. We will be discussing about the solution in our later video. So please try it out. Thank you.